Let's recall what a statistic means. A statistic is a calculation about data, and data is a value plus context. So remember when we were counting Melvin's feathers back in week 1? We counted that he had 11,490, which is a value, but everything else is context, right? There's these feathers, and what were they counted on? It was Melvin, and who verified it? That was 2 University of Michigan chicken scientists, and what day did we do this on? All of this context gives the number meaning. So one important aspect of context is, what was the measurement unit? When a statistic represents a measurement, we have to know the unit. So we know that Melvin had 11,490 feathers. The feathers are the unit. A unit could be how many people in Toronto did something interesting. You might hear 3 out of 4 dentists recommend a toothpaste. Dentists is the unit. Dollars, or whatever the unit of currency is where you live, is another popular unit. Or we might be talking about a temperature, in which case it's especially important to know, well, what scale are we using? And so here I have 2 degrees Celsius. Sometimes a unit can be quite unfamiliar, though. Here's an example of an advertisement I saw online. It was a targeted advertisement on social media for a device that seems to be marketed to treat post-traumatic stress disorder, or PTSD. And on the y-axis here, they have these numbers, which I guess are the PTSD level. Now, I am not somebody who specializes in post-traumatic stress disorder. I don't know how PTSD is measured, and so I don't know what these numbers are at all. I have absolutely no idea where they're from. And does changing by 5 units on this scale, what does that mean? Like, how many of these do you need to change before somebody starts saying, wow, my PTSD symptoms feel like they're getting better? I just don't know. So for me, this is a big warning sign. Like, I immediately start thinking, I really can't interpret this chart because I do not know what those units are. Now, another thing to keep in mind is that some statistics are not exactly measurements. They're derived from other statistics. So one example is smart scales. Smart scales are a kind of they're body weight scales that you can buy for your home, and a lot of them claim that they measure body fat percentage. Now, I looked into this a little bit deeper, and it turns out that it's actually extremely hard to directly measure body fat percentage. And your bathroom scale is not doing a direct measurement of that. It really is not equipped to do that. So what this actually does is it measures other things that it can from when you stand on it, and then it plugs those numbers about, I think it was about bioelectric impedance, so something about how electricity travels through your body, and it uses that number, puts it into a formula that's built into the scale's computer, and spits out an estimate of what it thinks your body fat percentage must be. Now, derived estimates like this are crucial for a lot of kinds of science. So in fact, in neuroimaging or brain imaging, we really can't directly measure what sort of brain activity is going on in a person who's, behaving. We really don't have a nice and easy way to stick something to measure your neural activity inside your brain while you're up and moving about and doing all sorts of things that we might like to study. So we have lots of measurement techniques that use things like blood flow or electrical activity at a very coarse level to try to estimate what regions of the brain are active during certain kinds of behavioral tasks, like listening to something or viewing a movie. And so this is how a lot of neuroscience is done. We often can't get the direct measurement that we want, so a derived estimate is basically the best we can get. So I'm saying derived estimates are imperfect, right? And it's important to know that whenever we're talking about them, we're not talking about a direct measurement. We're talking about a measurement that then is transformed via some formulas into an estimate for something else, and they can be of varying quality. In fact, it turns out that the bathroom scale example, a lot of these are regarded by people who study body composition as not particularly useful enough for anybody to gain information from at home. But in neuroscience, we are sometimes able to put together, experiments that still tell us something because we can invest in very high quality equipment and hopefully use statistical analyses that, appropriately handle the fact that we have some uncertainty, that we're not measuring brain activity directly. Now, another part of context is that numbers can have some flavors, kind of like ice cream, and here's what I mean. Some numbers are ratios. So 3 out of 4 dentists, half of all Australians, 4 times as many visitors as last year. All of these are secretly a ratio. And ratios are comparisons. They tell you the relationship between two quantities. 3 of the 4 dentists that we asked, half of all Australians, visitors this year compared to visitors last year, right? All of these are making a comparison. A number can also be a percent. Sometimes you'll see on the label of a package at the supermarket, now with 60% more juice. Now this is also secretly a ratio. 60% is the same as 60 in 100. And percents can also represent probabilities. So if you hear that there is a 70% chance of rain, this isn't really a measurement, right? We can't have, we can't measure exactly, like, I'm not sure how you would measure that directly, but this is a statement about things that could happen. It's saying that there is a probability of rain, and we estimate it around 70% chance. Another way of thinking about this is if we could simulate, today 100 times, 70 times, we would end up with rain. Percents and ratios can be trickier than they look. For example, here's one that I hear all the time. I'm not even sure where it comes from because I hear it so much. 50% of marriages end in divorce. So let's try to unpack this percent. Now, as best as I could tell from looking into this number, and I've put a good reference here for it, it seems like this statistic probably comes from a rough count that, at least, based on some data in the United States where I live, there was a time that for every 100 marriages occurring in a year, there were 50 divorces. So there were twice as many marriages happening as there were divorces. But what does marriage mean exactly, though? There's a really subtle distinction here that can be made. One way that we could think about marriages is just any marriage ending in divorce. The unit is a marriage. But one person could have several marriages throughout their life. On the other hand, we could be measuring people experiencing divorce in their lifetime. The unit is a person, not a marriage. And so that means that, actually, you either do or you don't experience divorce in your lifetime. You will either have experienced it or not, no matter how many marriages or non-marriages you've had. Now, by necessity, the percent of people who have experienced a divorce is lower than the percent of marriages that end in divorce. And just take a second to think about why that must be true, right? That people can have multiple marriages, and some people do have many marriages. So the percent of people who have experienced divorce in their lifetime is going to be lower than the percent of marriages that end in divorce. In this example, it turned out what was being reported, or the closest that I could find to a citation for that 50% of marriages end in divorce, is more about marriages. It's not actually about the chance that I will experience a divorce in my lifetime, or anyone else will, right? We're talking about marriages ending in divorce in that statistic. We're not talking about people experiencing a divorce, and those are actually different units. So to sum all this up, when you encounter statistics, consider asking yourself, do you know exactly what the unit means? Is the number a measurement, or is it the result of a calculation from some other measurements? Is it a ratio, a comparison, or is it a probability? And if the statistic contains a ratio, what exactly is being compared? Make sure you know exactly what the two numbers that are being compared are.